All right, so this talk is bringing Kubernetes to the edge with NGINX Plus. The reason why this talk is using NGINX Plus is because NGINX Plus has the API that I need in order to sync between Kubernetes and populate backends automatically in NGINX. So this talk, I'm going to give you a little bit of setup. How many people know what NGINX is? Did you come to learn about NGINX, or you know what NGINX is? Wow, a lot of people don't know what NGINX is? How did you end up here? To learn about NGINX? Are you guys developers? Ops people? So you don't know what NGINX is, you're not a developer, you're not an ops person. Sweatshirts? All right, so I'll do a bit of explaining. NGINX is a load balancer if you don't know, right? It sits on the edge, and one of the goals is to proxy traffic to a set of applications. Kubernetes is a thing that will allow you to set of applications using containers. So what I'm going to do is set up what a container is. Do people know what a container is? All right, great. So in this context, I want to be clear about something. Containers in this context are not a virtual machine, not something that replaces a virtual machine, but something that encapsulates your app into a box that we can use to automate further, right? So the goal here is you take your app, regardless of language it's written in. We specify a few things about our application runtime, the ports we need, CPU memory. I'm sorry, it's just kind of loud over there. And then we can actually put this in a unit we call a container. And in Kubernetes, we can have multiple containers in what we call a pod, and we can schedule that pod across a set of machines. The whole goal of Kubernetes that I want you to keep in mind when we're watching this, we're going to try to treat a cluster of machines like a single server, right? So there's a bunch of elements of distributed computing involved in this, and once we create those applications on this single logical machine, we're going to use NGINX to get traffic there. And the way we do this is leveraging things like service discovery and NGINX as a proxy to locate the applications as they're being scheduled and move around our cluster. So keep that in mind. What is Kubernetes? At a very high level, it's a container management, scheduling, and service discovery system. It's more of a framework, right? So this isn't a platform as a service like Heroku or Cloud Foundry. It's a couple steps below that. It kind of gives you all the hard parts dealing with like distributed systems, service discovery, and a deployment mechanism to provide you a set of APIs that allow you to kind of construct your own workflow. All the state in Kubernetes, so when you deploy something in Kubernetes, there's no scripts, there's no Ansible, no Puppet. You truly declare what you want. You deliver that declaration to the API server, and the API server kicks off a chain of events to get your state the way you want it. So in Kubernetes, we do have a collection of nodes, but we don't consider them important. So you don't deploy apps to specific hosts. Right? This is where things get a little bit different for people. On each of these machines, only thing we care about is their CPU, their memory, their disk space. We're just concerned about their overall resources. That's all we want out of the cluster. They're responsible for running three things mainly: Docker to set up the containers. The kubelet is what sets up things like the mount space, networking, and talks to Docker to create the containers based on your specification. Now, each node, there's also a proxy that runs on board, and we'll dig into that so we can understand how service discovery works. The next thing is this idea of a pod. Many people write applications that require multiple containers or multiple applications to form one logical application. So you can imagine if you're a Ruby developer, you may need something like NGINX, Passenger, and your Ruby application in order to complete the stack. And in Kubernetes, you can describe that as a set of containers that live in a single pod. When you're in a single pod, you have the ability to talk to the other containers over localhost, so you share a network namespace. There's this concept of a scheduler, right? So the idea here is that when we submit our apps, our description of our application to the API server, a scheduler will pick this up and find the best fit inside the cluster for us to run that app, right? So this is different than taking a spreadsheet and posting apps to a particular host. How many people have used the scheduler before? Right, like 3 or 4 people. The rest of you, if you're an admin, you're probably the scheduler. You're the person that picks machines inside your organization, and you say they run there. You probably keep a database, like a spreadsheet, to map those things and where they go. How many of you are on call for that particular duty? You're highly available. You're a highly available human scheduler. No vacations. In Kubernetes, the scheduler is pluggable. So if you really wanted to, you could turn off the Kubernetes scheduler and watch the endpoint and deploy them yourself. Probably a bad idea. And then we have this concept of a replication controller. The goal of a replication controller is to look at your specification. You can think of an auto-scaling group if you ever used Amazon's web services before. And the idea here is that we could have a babysitter for our applications. So instead of giving one app to the cluster and having the scheduler place it, we would give a definition of a template and how many copies do we want in our cluster. And the goal for the replication controller is to take that specification and stamp out as many copies as we specify. So you can imagine starting a replication controller with a count of 1 and then scaling as you need, right? And we'll see what that looks like in Kubernetes. So right now, I'm taking a single pod and replicating it across 3 hosts. Since we are using a declaration to specify application deployment, if one of the machines were to go down, then the replication controller will notice that there's no help status coming for that particular instance of our app. It will then create a new one from a template, and the scheduler will pick up the unbound pod and do the algorithm again to find a new home for it, right? So nothing talks directly to anything. They all just coordinate state. And then services is where the tie-in to NGINX comes in. So in Kubernetes, since all of these containers are free to move around based on the scheduler's decisions that it makes, we have no idea how to track these things. But in Kubernetes, since all of our applications have a set of labels, we can talk to the API server, do a label query, and get back a result of all the IP addresses and ports for applications, right? So this means that they will be dynamic. That's all the slides we have, right? So the rest of this is going to be live demos. Hopefully this internet connection works. If it doesn't, then I'll just sit here and hand wave a little bit. All right, so everything in Kubernetes is declarative. So what does it look like to deploy an application in Kubernetes? So what I'm going to do is we're going to start with a babysitter. I'm just going to deploy NGINX. And what this specification says is written in YAML. And here I have a set of labels to identify my particular replication controller. Again, this is the babysitter. Now, what I want to do is say I want to start with one copy of the app that I'm about to specify below. The selector is important because the babysitter needs to know what applications you should care about. So if I put out a template like we see here, here's a template, we're going to spin up an instance of NGINX at version 1.7.9. And what will happen is when this instance is created, it will be given this label called NGINX. So once it's deployed, the replication controller can start monitoring state of the cluster to see if it can find an app that matches that label set. If it does, it just hangs back. If it goes away, it will stamp out another one from that template. So those labels are important. Those labels have to be different per replication controller because they can start conflicting with each other. If you were to allow 2 replication controllers to monitor the same set of apps, they'll sit there and start spinning them up and killing them back and forth. So the API server protects from that. So to deploy this particular application from the spec, we can do kubectl. So kubectl is the official command line tool in Kubernetes. Everything I'm going to type on the command line can either be done through an API. There are also commercial vendors that have dashboards and GUIs that allow you to do this from a web console, but everything is API driven. That's something to keep in mind. So what I'm going to do now is I'm going to create an NGINX instance from that template. So what happens now is the API server receives my definition. Once it receives my definition, it's put into view to the scheduler. And the scheduler says, well, there's a pod that's not bound to any host inside of my cluster. The scheduler picks this up, and it runs through all the machines in my cluster. Now notice I didn't say what machine that I wanted to run on. And if you were interested on what machines I have, well, here's a couple of them running and the resources that they provide. But what the scheduler will do is scan this set of machines and figure out who's the best fit. And the best fit in this case would be maybe you have the least amount of memory being used, the least amount of pods running. Something will have you scored a little bit higher than the others. We pick one, and then the scheduler places the load. So once we do that, we can list a set of pods. Now, once we have a pod running, the replication controller will sit there and babysit it. Now, if you wanted to know more about this particular pod, you can describe it. So I can describe this pod by name. So here I get a bunch of events about the life cycle of the pod itself, but what we're concerned about There's a little bit of data here. So we have this pod named NGINX in a random string. It lives in my production namespace. I did that on purpose. Here's the image that it's running. Now, there could have been a chance that this could have been composed of 3 or 4 containers. If I needed a local mem cache, I was free to put it in the same pod, and they will be scheduled as an atomic unit. So the nice thing about that is you don't have to have race conditions where one thing is scheduled on one server, the next thing gets scheduled on a different one. Since you have a pod, they go as one logical step. The next thing is, here's the host that it landed on. So we see that the scheduler made a decision, and it chose node number 3. Why did it choose node number 3? Probably because at random, they all had the same score, and it just picked one so it can move on and make a decision. So once we have that in play, most people would say, well, how do you get the logs? If these containers can run on any server, how am I to troubleshoot this thing? So one thing you can do is you can use the kubectl logs command. So I'm going to get the name of the pod again. So what we'll do is say kubectl get logs. And we can tell those logs. Actually, it's just logs. So we'll grab these logs, but we don't see anything, right? And I do want to send traffic to this pod, but again, all the pods in my cluster right now have a private IP address. They're not accessible from my laptop. One thing that's nice about Kubernetes, I can actually use the API to do port forwarding. So I can talk to the API server. The API server will do a lookup to find the pod and establish a connection so I can actually interact with it from my local machine. Right, so let's do this now. So kubectl, port forward. And what we'll do is we give it a pod, and then we give it a bit of specification. We will say we want to port forward port 10,000 to port 80, right? We kick this off, and then we find the pod, and we start forwarding traffic forward. So at this point, I'm free to hit this pod on port 10,000. So I'll do a curl. And I'll do it on localhost because we're just forwarding from our local machine to the cluster. And we get the response from NGINX. If I pop over to the logs, we see our request that we got proxied to from the server. If this pod were to move, the same exact commands work. We do not have to track the machines that it lives on. The API server will handle this for us. So with our logging in place, you can also do things like exec. So imagine that you need to see maybe what the base OS or what file is on the server. We do not put SSH in our containers. That is a bad pattern and a waste of memory. With these containers, we can actually execute inside of the container's namespace to do things that we want to do. So if you can imagine, if we call kubectl exec, we give it the name of our pod, and then we're free to run commands. Like I can do cat etc OS release. So on systemd systems, we can get information about the operating system by doing that. So that goes into the container, talks to the API server, does a lookup, and does an exec into the container and pushes our standard out back to us. You can also do things like uname. And if you know anything about containers, you'll know that we're sharing our kernel. So here we see that this is running on CoreOS. It has a pretty modern kernel, 4.2. So you have all these troubleshooting capabilities. So Kubernetes makes it super easy to deploy things, right? And most people would say, I have configuration management, right? Like configuration management does that to me, right? Maybe I don't have the flexibility of a scheduler placing my loads for me, but it works well enough. The biggest issue that you end up with like configuration management systems and static assignment is resource utilization, right? So in order to explain resource utilization, I usually like to do it with a game, right? How many people have played Tetris? If you haven't played Tetris, I'm pretty sure your childhood was probably sad. But it's a very simple game. So in Tetris, what we're going to do is, you can imagine each of the blocks that falls are a workload, right? And each of those workloads needs a scheduling decision. We're going to make a scheduling decision based on the things that we see within the cluster. We're going to try to visualize what resources we have free and make a decision. So if you don't have a resource scheduler, and you proud yourself on having a one-click deployment, you can roll out your infrastructure with one click. How many people can do that? Like you run one command, deploy your whole infrastructure. This guy, you guys should meet him. He's probably doing an awesome job. So this guy was like, hey, I can do one-click deployment. I am awesome. So this is what one-click deployment looks like, because you do it fast too, so we'll go to level 9. You don't do this slow, you do it fast, right? So you go fast. So now you have workloads coming in and you do one-click deployment, you walk away, right? And all of those resources in your cluster are just being wasted. You're deploying fast as hell, but all your resources are doing nothing. So most people with a data center, even though everything's fully automated, you're at less than 10% utilization. Amazon recently announced their earnings on their cloud platform, like in the billions. That's thanks to you all, because you're probably using like 5% of your VM, and they can just overcommit. You know what they do when they overcommit? They build services like Lambda. And they say, hey, thanks for not using all your resources. We're going to charge you the same, but we'll also sell a new service back to you using your spare resources because you don't know how. So we solve this problem. We bring in a resource manager and scheduler into our infrastructure. Kubernetes is one of those things. So we play the game again. And this time, we're going to describe the cluster that we want our blocks placed in the most strategic way possible. We want the cluster to think. You're not going to write code to do this. The cluster knows how to do these things. All we need to do is give it our workloads. And here's what it looks like when you have a resource scheduler. Things get a little bit easier. Now, it is slower because it has to look up things, but it's much faster than what you're doing with your spreadsheet. So what we do is we start to strategize where pieces should go. So we look around and we start to place workloads somewhat in the same place. And someone would say, well, that's not an even spread. How come you're not placing it on all the servers? Well, this concept is known as bin packing. And what we do in bin packing is we try to pack our workloads onto smaller servers so we don't get fragmentation. The goal here is to leave room for a more important piece. Sometimes we get it right. And over time, if we do bin packing well enough, we save room, and when the right piece shows up, we schedule it to the right machine, right? And you end up in a much better world. You can't ask questions right now. I'm giving a talk. I take questions at Q&A. Right, so this is what your resource scheduler will do. It will examine the whole playing field and figure out where the next workload should go. It will also do things to optimize things for future workloads to leave space in the cluster. And then most people will say, well, I don't have a greenfield environment. I am not starting from zero, right? I actually have things in my infrastructure. So if that's you, you're probably, it's going to be harder. You have your automation tools in place, and you're not going to start from ground zero, right? So even if you bring in Kubernetes, you can bring some of your workloads over to Kubernetes, and it will fill in the blanks for you. You can actually add nodes to Kubernetes and say, well, I only want to use half of the CPU and half of the memory. And what Kubernetes can do is it can start sliding things and filling out the utilization of your cluster. So over time, you start to smooth things out. And as you move more and more things over to Kubernetes, you start to clean things out. Now, some of you say, I work at the enterprise. How many people work at the enterprise? Because there's like one of them, right? If you work in the enterprise, you're probably not allowed to innovate, right? If you get caught innovating, they make you leave in favor of buying something from a vendor. As a vendor, I love that. Just keep doing that. So if you're in an enterprise, you have a different problem, right? Everything's written in Java. So it increases the difficulty a little bit. They've chosen to put everything on Oracle. So it gets a little harder as well. So if you're in that situation, the truth of the matter is there is nothing Kubernetes can do to help you. You can't do anything. It's just not meant for those systems. So that's resource scheduling at a high level. If you consider all of your workloads and you allow yourself to examine the whole playing field, you can place your workloads in a very strategic way, therefore raising your server utilization. This will be a big problem for people that are concerned about this stuff in the future. And tools like Mesosphere's products or Mesos and Marathon, Kubernetes, they offer a solution to this. So we're past the stage of automation, right? That's just baseline at this point. You need to care about your resource utilization. Once you care about your resource utilization, it makes it easy to scale your resources. So imagine a world where you deploy your app and it has no resource boundaries. What does it do? It eats up the entire server and you can't even log in to troubleshoot it. So what we do in Kubernetes or in general with containers, we deploy apps with resource constraints in place, right? And what does that look like? So in Kubernetes, we can actually describe what our resource constraints look like. So here I'm going to describe a quota. And this quota is called prod. So right now, in this namespace that I've been operating in, I actually have put a boundary around the amount of CPU and memory that can be used in this cluster. So for consumers of this particular namespace inside of Kubernetes, this is all the resources they get to see. Even if I had a terabyte of RAM, this is all they can use. Another thing about resource scheduling that's important, you also don't want tiny workloads that are fragmenting your entire cluster. Because if you notice from our limits, here, we only allow 120 pods inside of our entire cluster. So if I were to allow a bunch of small pods to enter our cluster, we're going to run out of a resource first. We're going to run out of the number of pods that can run, And now we have a bunch of CPU and memory that goes underutilized or not utilized at all. So we want to put some limits in place. So what we can do here is we can say, if you do not specify a limitation, by default, we're going to set you to 1/10 of a CPU and 200 megs of RAM, right? And the goal here is to set these limits so that way we have even usage of the cluster as things get deployed. So once we do this, if we notice when I talk get pods, I didn't specify any resource limitation for this particular pod. If I were to look at the API, if I were to describe this pod, we'll see that automatically this system put in a resource cap, right? If I go to deploy a pod that's too big, it will be rejected immediately and the scheduler will not even take it into consideration. If you deploy things that are that don't have any more resources, that's not actually an error. Things will just spin in the background looking for free resources. On the back end, you're free to add another machine that has more CPU and more memory, and the workload will be scheduled at that point, right? So it allows a bunch of flexibility and separation of concerns. So once you have that, it makes it easy to scale. So in Kubernetes, we can actually look at our pod. So we're going to get our resource controllers. So we have this replication controller called NGINX, and right now we have one copy running. Let's say traffic starts to heat up, and the next thing you want is more copies of it. So how do you do it? So in Kubernetes, what we'll do is scale resource controller NGINX, and we can specify that we want to change the number of replicas. So what we're going to do here with this command is we're going to patch our specification in place to say I want you to go from 1 replica to 5. So we say we want 5. And what we can do once we do this is we can watch the events. So we can get all the events in the system, and we can watch them. So what's happening here, we can see that things are being specified, things are being created. They may have been created so fast that they're already done. I can verify this really quick, kubectl get pods. And we see that they're already running, right? So we can scale, it launches the containers, gives them their unique name, they get their own unique IP address. But we still have a problem. The problem is we cannot get to those private IPs from outside of the cluster. So what do we do? Well, one solution to this problem is to expose our service on a high port on every machine. So now we're going to get into service discovery. So we have all these apps running across the cluster. How do we find them? So one way we can find them is by doing label queries. And we can create a service. So here's the NGINX service, and it says it's going to track all, with this selector, any pod running that has a label called app equals NGINX, I'm going to send it traffic. I don't know what those are yet, but when I create this service, it's going to do a query to find them whenever someone hits this high port. So I'm allocating port 36,000 across all my hosts. If you come in on that port, you will be proxied to all the backends round robin. Right, so let's create this really quick. kubectl create -f services NGINX. So we create this service, and it gives me this warning and says, hey, you're going to allocate port 36,000 across all your servers. How does this work? So underneath the covers, I'm going to show you really quick because there's no magic here. We're just going to pick one of our nodes. It doesn't matter which one. So all of these nodes real time are listening to the API server for events. When that service events got created, all the machines near real time take their specification and go to work. One of the tasks that they were tasked with was creating IP table rules to intercept traffic on port 36,000 and proxy to pods. If we were to list IP tables rules, all right, so what we'll do here, we'll find some redirect rules that are put in place. Now this is a little hard to see, so I'm going to try to highlight it for folks. So here, this rule says, if anything comes in on port 36,000 to this host, we're going to redirect that traffic to a local proxy that's running that will then do a label query to the API server, get a list of backends, and round robin to them. The nice thing about this solution, even if that pod is not running on this server, it will still put you in the right place. You don't have to keep track of things. But if you notice the problem here, we're paying a double hop cost. We land on the host, our pod isn't there, we got to go back out. That's expensive, right? There's a better way of doing this. Let's put NGINX on top and teach NGINX how to talk to Kubernetes directly, because we still can't pin things to servers. We don't want to do that. We want to have something a little bit more elastic, a little more dynamic. So the way we can do this is, So one thing I want you to remember is this thing. Keep this in mind. Describe, service, NGINX. You notice the number of backends here? There's 3 IP addresses there plus 2 more. If we were to scale this, let's say we scale this to 10. The scheduler is going to go do its thing, make sure the right resources are available. If they're available, they get scheduled. And as soon as they get scheduled and become healthy, we describe again, and now we have 6. And as they become healthy, they'll start to grow. And now we have 3 plus 6 more, and then the other one's coming online. This is done automatically for us. And this is the nice thing about the dynamic queries. Now we need to teach NGINX how to do this. So how do we do that? So we have this service in place. We have an API endpoint we can talk to say, hey, give us all the backends for a particular label that we care about. It's called a label query. How would we do that programmatically? So let's jump on NGINX. So there's 2 things. One, in NGINX, what you're going to need, you're going to need some configuration. So in NGINX, this is one way of doing it. So in NGINX, I have this server declaration. And here I'm saying I have a backend called NGINX. So what I'm going to do is map Kubernetes service names to Kubernetes or NGINX upstreams. And what I want to do is ask Kubernetes for a list of backends, and I want to push them into an NGINX upstream. Now, the thing I like about this solution is I do not want to rewrite files, right? That pattern works, but it is cumbersome. What I want to do is talk to an API to say, hey, I have some backends, and I also want to sync those backends. I only want to remove the backends that don't need to be there. And I do not want to start NGINX to do this. So you use something like NGINX Plus, and it gives us all the semantics. So with that in place, what we can do is deploy a tool called Motorboat. And really quickly here, I'm going to show you the code for Motorboat. It's really tiny, well, tiny in my regards. But if you look at Motorboat, I'm going to jump down here in main. We're going to do 2 things. One, we're going to watch the endpoint of Kubernetes. So that watch command that I did on the command line, I can actually open up a WebSocket and say I want to watch for all events for endpoints. And as I get that data, I can do something with that data. Things will be added, things will be removed. So once I get that data, I can do an infinite loop, get the NGINX status to figure out what the backends look like, and then I can start to synchronize from Kubernetes to NGINX. I think I'm running out of time here, so I'm going to just skip straight to the deployment. So that's Motorboat. It's a Golang binary. It is available on GitHub. You can pull it down and check it out. Now I need to deploy Motorboat. Again, I'm just going to use a replication controller. So I have a replication controller called Motorboat. It takes some configuration arguments. Where's the API server? Where's NGINX so I can make my API calls? I'm going to deploy this thing. Before I deploy it, let's take a look at our NGINX console. All right, so here's my NGINX dashboard. There's nothing there, right? So what I'll do is deploy Motorboat, kubectl, create-f, rc, Motorboat. And what happens now, Motorboat goes, talks to Kubernetes, does a label query, sees that there's a service called NGINX, talks to NGINX, finds an upstream called NGINX, matches the 2. So at this point, we have 10 backends, right? And the nice thing about this solution is that if we were to scale, this down to 5, notice what happens here. So right now there's 10, and almost instantaneously they get removed. And the nice thing about having NGINX in front, if any of those pods are unhealthy, NGINX will do the retry logic. There's no need to rebuild that from scratch. NGINX will handle the idea that, hey, that pod went away, let's retry the request. And now we're talking directly to the pods, and now we're dealing with these containers as first-class citizens, and the host is no longer important. If the host dies, the container moves, the container gets updated in the back-end service, and then we sync. So with that, I'd like to end my presentation. Thank you. I think we have time for Q&A. Some guy had a question. This is now the right time. Ask your question. The question is, do you still need a load balancer? The question is yes, right? Because your alternative is to take all those IPs, which will be right for about 5 seconds. Things get moved around. So the load balancer does a couple of things, right? One, it spreads the load and does some healing properties. So if something goes away, we retry. And we do want to spread the load across our pods. So putting NGINX in front gives us that load balancer, right? We want the load to be spread across all of our pods. Right, so the question is, in this scenario, do I have a way for the load balancer to be highly available? So let's talk about the pattern there. So the tool I have, Motorboats written in Golang, is pretty easy for me to add a bit of concurrency. So if I had a list of NGINX servers that I wanted to synchronize, I can just do them all in their own Go routine or in a separate thread and just push the bits to them. So now we have, let's say, 3 independent NGINX machines that are being synchronized. And then the pattern, what most people will do is you will have something like either DNS where you just alternate, you give equal weight to each IP. And some DNS servers are smart where they do health checking. So if a backend goes away, you remove that IP address out of the loop. Some people have smarter things where they do maybe something a little stronger at the edge, like an F5 that has a little bit more redundancy that you proxy back to NGINX. There's a lot of patterns of handling NGINX high availability at that layer, but most patterns involve you just synchronizing all of the NGINX machines independently, and something that's up top handles the round robin of traffic up front. Question? How do you generate configuration files? What configuration files? NGINX configuration files? The YAML files. Great. So the question is, how do you generate the YAML files? They got this new invention called the keyboard, and you just type them out. Yeah, so there's a specification on what can go on them, right? Let's say you don't want to type. Let's say you're brand new to Kubernetes and you do not want to type out this YAML file, right? How do you do it? So in Kubernetes, we could do something like kubectl. I want to just run. I want to run, let's say, MySQL, and I just want to use the image called MySQL, right? I don't know if this is going to work, but if I run this command, I should get MySQL running in my cluster. So let's try it. I hit run, and then it goes out, and it builds the specification for me automatically. So now if I do kubectl get pods, I see that NGINX is running, or MySQL is running in my cluster. If I do a kubectl get pods, and then I get NGINX or MySQL specifically, I can do output equals YAML, and we see the whole definition that we would write by hand. So some of this is metadata that you get from the Kubernetes kubelets that run the machines, giving status updates that it is running its ID, but there are some things that are actually just metadata, like here's labels, here's the name that it gave it, it's in this namespace, here's the specification for it, here's the container, and here's some other policies, and notice the resource limits get decorated automatically from our limits. So you can actually run commands that will set this up for you, and let's say I needed a service for this. I could also do kubectl expose rc MySQL, and if I do that, port, what is the default port for MySQL? 3306. So with that, now I actually have a service IP for my container, even though I don't know where it's running, right? So all these things can be done without actually touching config files. The reason why you want config files, though, is you need to kind of have a way of articulating to people what the state of the cluster is, right? So today, everything lives in etcd, and etcd is designed to be highly available. But one thing you need to understand, if you delete your etcd database, in about 5 seconds, your cluster will be empty, because the new state is delete everything right away. And all of your machines will go to delete everything right away. So you got to be careful with that. Good question. So the question was, in this case, the NGINX config will not have any upstreams in it. So let me just show you what that NGINX config looks like. So if we do NGINX, you notice I just have an empty set of backends in my upstream. So what I'm doing here, and this is just a pattern that I picked for myself, is, hey, I have a set of upstreams. They get a little bit of memory to hold their in-memory representation of the backend state. I start it up, and now everything that I need to interact with NGINX will be available through the API. One thing I would like to see in NGINX Plus would be the ability to create it upstream, right? So I don't think you can create an upstream from the API. Because if I had that, then I don't even need to do this prep work. I could just launch a raw instance of NGINX, programmatically add an upstream, add the backends, delete the service, delete the upstream, and it all works. So if we had that ability, it would really probably be a much more dynamic system. It's like magic, isn't it? So the question is, how do you control what the apps do when you put them in containers? You can't control what the apps do when you put them in containers, right? If someone writes code that says, I'm going to try to reboot the server, well, the good thing about containers is that most syscalls are disabled, right? You try to run reboot, it's gonna be like, you can't do that, right? If you try to do things like call a syscall that in the config, so you actually, all the things you can do in Docker as far as what's enabled and what's not enabled, you can do that in Kubernetes as well. So, all right, so you're the app writer. So you wrote the applications and someone gave you a namespace, right? Say, hey, go to town, here's your resources. What you would do is either do like the run command or you would follow the documentation and say, hey, how do I create one of these things? So let's look at a replication controller. So for NGINX, or let's look at Motorboat because that has a little bit better definition here. So for Motorboat here, I'm saying, look, I want this thing to always be running. So this is why I'm going to use a replication controller and not just a pod. So I always want it running. You know what? I only want one of them running. You could put 5 here and say, my intent is that there will always be 5 copies. The next thing you could do is say, the labels are nice because that gives you a way of finding things. And when you start to create services, it gives a way to services to find your backends, right? So that's what you're going to do with your labels. And this is where the sysadmin team may jump in and say, well, we want to tweak that a little bit. Now, you notice that I don't have memory here, but if you were to submit this to the cluster, you would automatically get a set of CPU and memory constraints. Those are done through what we call emission controllers. So admins can actually do something where before it touches the API, I can filter and adjust things. So if I notice that you're touching an image you shouldn't be, I could build a emission controller that says you can't pull images from there, right? The next thing I can do is say, hey, here's my image name or the image ID I want to use, and then here's the flags that go to that image. I can also declare things like volumes. So one thing we didn't talk about in this talk, if I needed a persistent disk in GCE or Amazon, I can actually say, I need this volume, and it needs to be a persistent disk. So when I go to get scheduled, the persistent disk will be created for me, attached to the server, and bind mounted in place for my container. You can specify all those things here. Good question. So the question is the Docker file for Motorboat. So one thing that's nice about Golang, when I build binaries in Golang, I tend to statically link them, right? So in Go, what I can do is, since I'm on my Mac and I need this binary for Linux, I can do go os equals Linux, go build, and I hit this button, and what I end up is a statically linked executable. That means I don't need libc on the other side, no runtimes, I don't need anything. So if I look at this binary, it's going to be quite large. It's 6.9 megs, right? So the Motorboat application is self-contained with its own runtime, 6.9 megs. What does the Docker file look like? So all I need is the scratch container, meaning I don't want an operating system, no Ubuntu, nothing, right? And then the next thing I want is just to add my binary into the image, and then I'm just going to put it at slash. So my entire image is about 6.9 megs, and it makes it much easier to scale these around. Some people do not think that a gig image is a problem. It is a problem. If you have an image that's a gig in size, there is a much better way of doing it. Scan YouTube, there's tons of examples on how to do that correctly. Is that all the questions? Awesome, so I hope you guys would enjoy Kubernetes. I think you should check it out. And also think about things of leveraging APIs because that is the new shell scripting, right? We're gonna move away from the server and we start to leverage more powerful tools to do this stuff. Thank you.